In the last class, we talked about conditional probability. Conditional probability of event E when F has already occurred was given by PE by F. And we wrote PE by F as PE intersection F divided by PF. That's what PE by F was defined as. Okay. Similarly, PF by E can be written as PE intersection F divided by PE. Okay. Now from this result, we can write the same result by cross multiplying these two things. So we can write PE intersection F into 1, that is PE intersection F, is equal to, then these two things get multiplied. So PE into PF by E, this one. And also we can say cross multiplying this thing, just cross multiply it, and you get PE intersection F is equal to PF into PE by F. Say this is an urn. It contains 10 black balls and 5 white balls. All right. So this is a beautiful urn. Now, two balls are drawn from the urn, one after another, without replacement. What is the probability that both balls are black? So we can take two events now. Say the event E, that the first ball drawn is black. Okay, and I can take the event F as the second ball drawn is black, right? Second ball drawn is black. What will be the probability that it is a black? I can see here, PE, first ball is a black. I have 10 black here. The total number of balls is 15, 10 plus 5, right? So that is 10 by 15. And what will be the probability? Now the second ball, once the first ball is drawn, my urn will look like now this. See, I'll have 9 black here and 5 white. So F by E will be now 9 by 14. So I'm asked, what is the probability that both are black? What does this mean? Means we are asked to find E intersection F. Here you see. So we'll define E and F respectively the event that the first and second ball drawn are black. So okay, here we write PE is equal to, say this was 10 by 15. F by E was 9 by 14, and PE intersection F will be 10 by 15, can also be written 2 by 5, 2 by 3, yes, and 9 by 14. So 2 by 3 into 9 by 14. So this is 6, 3, and this is 7. Okay, so it comes out to be 3 by 7. Now, let's consider a question here. Three cards drawn successfully without replacement from a pack of 52 cards. What is the probability that the first two cards are kings and the third card is an ace? So if you look at the deck of 52 cards, we know how many kings are there and how many aces are there. There are four suits. Every suit has one king and one ace. Now, what will be the probability of getting the first card as king? If I say PK, that the first card drawn is a king. Obviously, because I have four kings and total number of outcomes are 52, 4 by 52. Now, what will be the probability that the second card is a king given that the first card drawn is a king? Now, without replacement means if we draw the first card as a king, we will not replace it. Now I have three kings and the rest all cards are there. So that means the total number of 51 cards I have. Out of 51, 3 are favorable. So PK over K will be 3 by 51. Okay. And the third one is ace. That means P A over KK. KK means first two cards drawn are already kings. So the two kings are gone. Out of 52 cards, two kings are gone. 50 cards are left. Okay. Total number of 50 cards are left. Out of those 50 cards, how many aces I have? Four of them are aces. So the aces favorable is 4. Total is 50. So this comes out to be 4 by 50. Okay. 4 by 51, 3 by 51, 4 by 50. Okay. Now what he is asking? He is asking to find the event occurs in this order. P, K, K, A. P, king, king, ace. That's what he's asking, right? So we'll apply the formula. So this is actually the product of these three. This into this into this. The pk will be how much? The first card king is 4 by 52. And then we said pk by k. K by k means the first card is a king, then the second card is a king. Okay. That was 3 by 51. And then one more thing, P, the third card is an ace when the first two has come king. So this was like I had four aces left, out of which the total number of cards were 50. Once two kings are drawn out of 52 cards, obviously I have 50 cards left. And out of which four aces are still there. Just remove two kings, right? That's why it is this. So what we are asked here, we are asked PKKA, PKKA. So PKA will be PK into, we'll apply the multiplication rule. So PK over K, it means the if first is king, then the probability of the getting second king, and third PA over KK. What does it mean? It means first two cards drawn are king, then the third card is an ace. So this is, if we put the value, it's like 3 by 51 into 4 by 50 and into what was P? 4 by 50, 3 by 51. I had 4 by 52 there. 4 by 52. First value was 4 by 52. So 4 and 52 should be cancelled. 4 1 4, 4 13. Okay. And 3 and 51. It's one time and 17. And this should be 2 and this should be 25. All right. So it comes 2 divided by double 525 is equal to 2 by double 525. So, okay, so we got the probability of drawing first two kings and the first two cards as king and third card is an ace will be 2 by double 525. Here we go. So a card is drawn from a deck of 52 cards. E and F denotes the event of the card drawn is a spade and the card drawn is an ace. Find P, PF, PE by F, PF by E. Okay, so let's try to find all these. So if E is the event that the card drawn is in space, card drawn is in spade, and F is that it is an ace. What will be PE? We can see here. PE will be how many spades are there? 13. 13 by total are 52. So it's 1 by 4. Now let's see what is PF. Now PF, the card drawn is an ace. There are four aces, four, one in each suit, right? 1 by 4 by 52, 1 by 13. Now let us find PE intersection. Let's find E intersection F. So how many elements are there in E intersection F? Means the card should be an spade and it should be an ace, spade and ace. So there is only one ace in the spade suit, right? 1 by 52. So we got these things. Now can we find PE by F? Let's see. So E by F, probability of occurrence of E when F has already occurred By definition, that is PE intersection F divided by PF, that we learn in conditional probability. So which comes out to be 1 by 52 divided by 4 by 52. 1 by 52 divided by 4 by 52. So which is same as 1 by 4. Notice one thing here. PE was also 1 by 4 and PE by F is also 1 by 4. Similarly, let us see what we are getting PF over E. PF over E by definition will be PE intersection F divided by such event when PE by F is equal to PE or PF by E is equal to PF are called independent events. Now, independent and mutually exclusive, these two terms, right? Sometimes we confuse between these two terms. They do not have the same meaning. When we say independent, it is in terms of probability of events. And when we say mutually exclusive, if you could draw mutually exclusive, we have learned in set theory, mutually exclusive means there should be nothing should be common in between these two, right? Whereas in case of independent events, there will be something common. That's how we'll find E intersection F, E intersection C should be PB into PC. And also PA intersection B intersection C should be PA into PB into PC. For 3 events, we need to verify all these 4 things. Next, let's take one example here. A die is thrown is the event. The number appearing is a multiple of 3 and F is the event that the appearing is even. Find whether E and F are independent. So we find the events E and F. Number appearing is a multiple of 3. Come on, multiple of 3 would be 3 and 6. And the F is defined as the number is even, right? So the F will be event like 2, 4, 6. From there, we can calculate E intersection F. Okay, fine. So what will be E intersection F? E intersection F would be, what is common over here? 6, all right? From this data, we can find PE. PE will be, there are 2 favorable outcomes and total is 6, 2 by 6. It should be 1 by 3. And we can calculate PF also. So PF in this case will be favorable outcome for FR3. F was even, right? So that is 3 by 6, which will come out to be 1 by 2. Okay, what would be PE intersection F? PE intersection F will be, in this case, what are the common element? I have only 1. So 1 is favorable, 1 by 6. So let us see what is the product of PE into PF. So when we see PE into PF, we observe that it is 1 by 3 into 1 by 2, which is 1 by 6. And eventually it is same as P intersection F. So I can say is equal to PE intersection F. So this means E and F are E and F are independent. Independent. Okay. Now we have another question. An unbiased die is thrown twice. And let A be the odd number on the first row and B is even number on the second row. So we have defined 2 events A and B. Check the independence of A and B. First of all, we would like to write the sample space for this experiment. Our sample space, we know there will be 6 into 6, 36 cases, because let's write it this way then. NS, number of element in the sample space, would be 6 into 6, that will be 36. So we can also write all those 36 if we wish, but not needed to write all those 36. We can write event A. How will event A look like? Okay, he's defining odd number on the first row. So odd number on the first row means you'll have like 1, 1, 1, 1, 1, 2, 1 3 1 4 1 5, so it come up to 1 6. Okay, and then it will be like 2 1, no, not 2 1, 3 1, because odd number on the first row. 3 1 3 2, and so on and so forth. It will go up to 3 6. And also I'll have like 5 1 5 1 5 2, and go up to 5 6. All right, so we see 6 6 6, 18 element in A. So let's see what we have in B. A B event will also be like event B, and event odd number on the second row. Odd number on the second row will look like this way. See, on the first it can be any number, but on the second it should be odd. So 1 1 2 1 3 1, and go up to 6 1, right? And then I'll have odd on the second, means now I'll have 3. The second odd number on the second can be 3. So that is 1 3 1 5 1 7. Sorry, 1 1 3 2 3, so on, right? 1 3 2 3. Okay, like that. 1 3 2 3, and it goes out 6 3. And the third odd number on the third can be like 1 5 2 5, and it goes up to 6 5. Okay, that's how the odd number can come. On the second one, we should have odd number. So this will be event B. So what is A intersection B? Let us write A intersection B. We see there are 18 element in this, there are 18 element in this. So A intersection B means on both the dies we should have odd number. How many such cases can be there? So it will be like 1 1, odd on both, right? 1 1. Then it will be 1 5, 1 3, sorry, and 1 5. Three element will come from the first row, and then I can have two. I'll have not, so 3 1 3 3 3 5. So 3 1 3 3 and 3 5, like this. And then I can have 5 1 5 5 5 3, sorry, first 5 3 and 5 5. 5 1 5 3 5 5 5 3, and then 5 5. So this is all. We can have 9 element. So an A intersection B is equal to 9. So if we see here, what would be PA, probability of occurrence of A? We see this is, there were 18 cases, right? 18 by 36. So it is 1 by 2. What is PB in this case? PB is, again, there were 18 cases. So 18 by 36, again 1 by 2. And what is PA intersection B? The A intersection B is also, you see, there are nine cases. No, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 favorable outcomes. Total number is 36. So it is 1 by 4. Now see, 1 by 2 into 1 by 2 is actually 1 by 4. So that means here what we can say, PA into PB is equal to PA intersection B. That means these two events are independent. So once you have done this much, we can, the next step will be, in this case, we can write PA into PB is equal to 1 by 2 into 1 by 2, which will be 1 by 4, and which is same as PA intersection B. That means, therefore, A and B are independent. Independent. Okay. Yep. So this is done. A and B are independent events. All right. Next, 3 coins are tossed simultaneously. Consider the event E. So if 3 coins are tossed, we know that we can write the sample space first of all. The sample space will look like three coins tossed, all three heads. Now I can have two head and one tail. Now I can keep shifting this tail, position of this tail. So head, and then a tail comes at the first. So this is how it can happen. Then I have two tails and one head. Then I can have tail. I will move this head in a different location. So head comes at the first position, and finally all three tails. Okay, so these are the total outcomes. So there are nine. So so event E is what? E is defined as three tails, right? Three heads or three tails. So that means E contains three head or three tails. This is event E. How is F defined? F is defined as, you see, at least two heads. So at least two head means it will have three head also, and two head and tail, and head and tail head. This is at least two heads, and EF and Z. One more event is there, Z. So Z was defined as at most two head. At most means we can have two and less heads, right? So all that contains two head will be there. Except this, I'll have all. This I cannot have. At most two head means more than two head are not allowed. So all these. So double HT, HTH, THH, TTH, THT, okay, so H double T and triple T. There are seven elements, okay, at most. Of the pair EF, EZ, FZ, which are independent, which are dependent. So if two events are independent, we know the condition for that. As the events are not independent, they will be dependent. So let's check for each. So PE is what? Let's see PE. How many elements are there? Two. So it will be like 2 by 8. Total are 8, right? And what is PF? PF will be F. I have 1, 2, 3, 4. That will be 4 by 8. 1 by 2. And PZ will be how much? PFZ 7 by 8. Oh, we need to find E intersection F, and we need to find E intersection F first. How much is E intersection F? We see triple H is common here. So if I write PE intersection F, I can see only one element is common, HHH, if we could see, right? So P intersection F means this thing, this, sorry, PE intersection F we are talking about. So triple H and triple H here, these two are common. So the probability of P intersection F will be 1 by 8. Similarly, what will be PF intersection Z? F intersection Z will be, now what is common in F and Z? If you could see, F and Z, what is common? HST is common here. HST, HST, HTH, HTH, THH, THH, right? So E and F has three elements in common. So it will be like 3 by 8. What would be the probability of uh, EF, FZ? Now we can find EZ also. E intersection Z. E intersection Z, if you could see, E and Z, what is common? Let's see what is common in E and Z. Here we go. I think HHH, TTT. So HHH is not in Z, so just one element. Here you go. TTT, TTT. Nothing else is common in E and Z. So this is 1 by 8. Now let's see which of them are dependent and which are independent. If we see PE into PF, what do I get? PE was 2 by 8, which is 1 by 4. PF was 4 by 8, that is 1 by 2. Okay. So PE into PF is actually 1 by 8, 1 by 4 into 1 by 2. So we can say E and F are independent. Okay. So here you can actually write PE into PF. PF is equal to 1 by 4 into 1 by 2. That is 1 by 8. So it's same as PE intersection F. This means E and F are independent. This means E and F are independent. Similarly, you can check for others, and you will observe that these two are not independent. That means they are dependent. Which two? You can check for F and Z and E and G, right? So here first we will conclude this. E and F are independent, and you can check for other two events and you'll find that other two are not independent. Okay. Let's see what we have next. E and F are independent events, so are E and F complement. Now, about E and F complements, what we know, the two event E and F are, if they are independent. So how do we say if E and F are independent? Let us first try to understand event E and F with the help of Venn diagram. Here we'll draw two event E and F, right? So suppose this is an event E and there is another event F, right? So what we have, this thing was E, this thing was. So obviously this part will be E intersection F over there. Now what we are talking here is if E and F are independent, that is given. That means what we are given is PE intersection F is equal to PE into PF. This is given since they are independent, right? Since E and F are here in region, I'll write E and F are independent. Okay. Now, how can I show E and F complement are also independent? For that, see, can we write, so this part is E intersection F. If I could show this part, the one we have shaded, this part is E intersection F. This part is E intersection F. The part over here, this is E. So the outside E will be E complement and outside F will be F complement. So the outside part, the one which is outside both the circle, will be E complement intersection F complement. How can we show that? That place all of outside this will be written as E complement intersection F complement. Now, how can I write the event E? Event E intersection F complement. So what will be the E intersection F complement thingy? Let's say E intersection F complement is everything F, outside F, right? So this portion here in pink will be E intersection F complement, right? So if I add E intersection F complement and E intersection F, I get E. Can I write here um, probability of E is equal to probability of E intersection F plus P E intersection F complement. From there, if I bring this P left and I take this right, I mean just shift these things. I want to know P intersection F complements. I will get PE intersection F complement. From the Venn diagram, it must be very clear because this portion, the portion in pink over there, is E intersection F complement. Portion over there is E intersection F complement. We need to show about E and F complement, no? That's why we are relating this with E intersection F complement. This thing will be PE minus PE minus PE intersection F. This equation can come like this. From there, PE intersection F is PE into PF, so which can be written as PE into PE into PF. Sorry, here it is minus. PE into PF will be same as PE intersection F. Okay. Now this means if we take PE common there, what do we get? We get 1 minus PF. And we know 1 minus PF from our earlier discussion that PE 1 minus F will be PF complement. So this is PE intersection F complement. Okay. So PE intersection F complement is coming. This is same as PE into PF complement. PE into this thing 1 minus PF will be PF complement. PE into PF complement is PE intersection F complement. And this statement over here proves that therefore E and F complement are independent. E and F complement are independent. Okay, so this is how we prove two events E and F are independent, then E and F complement are also independent.